FactSage is already widely used for modeling metallurgical processes. This demonstration shows an example for the strength of thermochemical software in metallurgy. It is shown under what conditions silicon dioxide can be reduced in a carbothermal process. A website offering free but limited thermochemical calculation abilities is the FactWeb. Here you can test some basic functionality of FactSage. For example, to describe carbothermal reduction of silicon dioxide, ReactionWeb can be used to calculate an Ellingham diagram. Such an Ellingham diagram is shown here. The standard Gibbs energy of oxidation is shown per mole of oxygen for silicon and for the three reactions involving carbon. It can be seen that there is a crossover at around 1700 degrees C. Above this temperature, it is expected that silicon dioxide can be reduced by carbon, forming silicon and carbon monoxide. Now, FactSage is used to demonstrate why the Ellingham diagram is an oversimplification and under what conditions silicon dioxide can be reduced to metallurgical grade silicon in a carbothermal process. In the FactSage user interface, you can find options for general information, database information and database management, the various modules for thermochemical calculations, and options to handle the results. Since we are interested in the equilibrium phase composition that results when silicon dioxide and carbon are allowed to react above 1700 degrees C, the Equilib module is used. When we start the Equilib module, FactSage automatically asks whether the last system should be loaded. This is practical if complex calculations are continued. Here, we want to start a new calculation from the scratch, so we select No. For any thermochemical calculation, a database has to be selected. Many users work mostly with the same database, so the database selection step can be omitted. Since we want to start an Equilib calculation from the scratch, we will select No, and the data search window will be automatically opened. Here we find the standard databases that are available in FactSage. There are many databases, and information on the databases can be found on factsage.com under Database Documentation. Your FactSage agents around the world will also assist you to choose the databases that fit your needs. For the current example, we will use the SGTE Pure Substance database. One could have also chosen the FACT Pure Substance database. After choosing the database, we are directed to the reactants window of the Equilib module. Here we will define our starting material. Since we have two reactants, silicon dioxide and carbon, we have to add a reactant. The first reactant is silicon dioxide. The Ellingham diagram suggested that we should mix silicon dioxide and carbon in a mole ratio of 1:2. So we will insert 2 mole of carbon as second reactant. If we, for example, wanted to insert our starting material in grams or pounds, we can open the units window. Here we can change units of temperature, pressure, energy, mass, and volume. Pressing Next directs us to the menu window. In the menu window, we can see what reactants we entered. We will have to define all the possible products and the calculation conditions. Since we do not want to restrict the possible products, but want to determine the global Gibbs energy minimum without kinetic restrictions, we will select all gaseous and pure condensed phases. We see that there are 26 possible species in the gas phase, 3 pure liquids and 13 pure solid phases. To check what these species are, we can right-click on the checkbox. In the gas phase, there are atomic and molecular silicon, carbon and oxygen, as well as molecules consisting of oxygen and silicon, carbon and silicon, or carbon and oxygen. With the current selection, we allow the formation of any of these species, and in the output, we will see what are the individual concentrations. There are 3 pure liquid phases, which are silicon dioxide, silicon, as well as carbon. In the solid state, we allow the formation of silicon dioxides in various crystal structures, alpha and beta silicon carbide, pure silicon, as well as carbon as graphite or diamond. Since we selected a pure substance database, there are no solution phases that can form. Now we only have to set the conditions under which we want to know the equilibrium phases. Since the Ellingham diagram predicted carbothermal reduction of silicon dioxide above 1700 degrees C, we will start at 1800 degrees C here. We will work with a pressure of 1 bar and start the calculation by clicking on Calculate. In the results window, we can first see the calculation conditions and then a table with the resulting phases. First, the gas phase is shown, and we can see that it consists mainly of carbon monoxide and silicon monoxide. Scrolling down, we can see the amount and activity of the condensed phases. The only condensed phase that has formed is actually silicon carbide. That phase was not even considered in the basic thermodynamic reaction approach of the Ellingham diagram and highlights the benefit of global Gibbs energy minimization performed in the equilibrium module. Below the list of phases, we can obtain the basic thermodynamic properties of the equilibrium mixture of phases under the calculated conditions, which are heat capacity, enthalpy, entropy, Gibbs energy, as well as volume. Since we are interested what we have to do in order to obtain metallurgical grade silicon, we will change calculation conditions in order to see what we have to do in order to obtain silicon. For this, we go back to the menu window, which can be done by clicking on the button showing fork, knife and spoon. First, we will vary the temperature from 1800 degrees C to 2800 degrees C in steps of 20 degrees C. For this, we simply type in the temperature field the start temperature, end temperature, and the step size. If we are also interested in exact temperatures of phase transitions, we choose the normal plus transitions option. Now 51 calculations plus calculations of transition temperatures will be done when we click on Calculate. We now find several pages in the results window. In total, there are 54 pages. While we could look at each calculation result subsequently, it is easier to prepare a quick graphical representation of the results. For this, we click on Output and then Plot Results. In the results processor, we first have to define the axis. We want to plot moles as a function of temperature. And we use the automatic axis scaling. Now we need to define what species we are interested in and click on Select Species. In the table we can find the species in the gas phase, as well as the individual pure condensed phases and the elemental contents in solutions. A species of interest can be selected by clicking in the first column. In our case, it is practical to use the shortcut and select all stable phases. Now we only click Plot and the graph will be shown in the figure module. As we can see, the gas phase is the dominating phase over the whole temperature range. Silicon carbide is the only condensed phase up to 2300 degrees C where liquid silicon starts to form. The figure can be easily modified in the figure module. For example, all lines can be modified at the same time. Of course, the diagram can be saved for later use. Pure liquid silicon without silicon carbide is only obtained above 2620 degrees C, which is an extremely high temperature. In order to reduce that temperature, we can now quickly adjust the carbon to silicon dioxide ratio in the starting material. For this, we go back to the reactants window. Since we want to reduce the silicon carbide formation, we drastically decrease the carbon content to 1.3 moles. Then we proceed to the menu window, where we do not change anything, but simply start the calculation. We will now repeat the plot of mole versus temperature and directly obtain the diagram. As we hoped for, we can see that the region for liquid silicon formation has increased significantly, and we can now obtain silicon without silicon carbide already at 2130 degrees C. For graphical comparison, we will superimpose this figure with the previous one. So we use the superimpose option and load the last file. The dramatic change is immediately visible. Obviously, there is a drastic reduction in costs associated with decreasing the furnace temperature from 2620 degrees C to 2130 degrees C. This tutorial has shown the enormous benefits when using FuxStage for metallurgy. In case of questions, please contact us.
FuxStage is already widely used in modeling. FuxStage is already widely used for modeling. Fact stage is already widely used for modeling. Fact stage is already widely used for modeling. Hi. Fact stage is already widely used for modeling. Hi.